Hello, we were talking about the main principles of machine learning. Now we are going to talk about regression. Alright, let's get started. Regression is one of the supervised machine learning techniques. It's a statistical method that allows estimating the relationship between input and output. Input is dependent variable and output is independent variable. Regression has lots of areas of use, such as weather forecasting, the relationship between advertising expenditures and sales, estimation of the price of the house according to its features, analysis of the relationship between income and education level. There are regression types such as linear regression, nonlinear regression, and multiple linear regression. For now, we will only talk about linear regression. Linear regression is a statistical method used to model the linear relationship between a dependent variable and one or more independent variables. It's frequently used to understand the relationship between variables to predict numerical values and to explain one variable with others. It's shown as y equal wx plus b. Y is the dependent variable, x is the independent variable, and b is the bias. Bias is the error term. W is the amount that variable x affects y. We can think of it as weight. Since there is only one independent variable x in this formula, it's called univariate linear regression. The type of regression that uses multiple independent variables such as x1, x2, x3 is called multivariate linear regression. In this video, we will focus on univariate linear regression. With this example, let's examine the relationship between the amount of rain and the number of umbrellas sold. Here, independent variable is the amount of rain, and dependent variable is the number of umbrellas sold. As can be seen, there is a linear relationship between these two variables. That is, when one increases, the other also increases. The original values in the chart are shown as blue dots. A linear red line has been drawn to represent all these values. The line segment is drawn using the least squares method so that the sum of the bias values is minimum, so the margin of error is minimized. There are various metrics to use to evaluate the performance of regression models. These metrics measure the difference between actual values and the model's predictions. Commonly used metrics are MSE, RMSE, MAE, and R-squared. MSE means mean squared error. This metric finds the average of the squares of errors between actual values and predictions. It's a metric where major errors are emphasized more. RMSE means root mean squared error. This metric takes the square root of the MSE value. This is a more interpretable metric. MAE means mean absolute error. This metric finds the average of the absolute errors between actual values and predictions. It doesn't perform squaring, so it is less sensitive to large outliers. A high value in these three metrics means a high error. Let's also look at R-square. The R-square metric expresses the ratio of the independent variables to the total variance on the dependent variable. A value approaching 1 indicates that the model explains the data well, meaning the error is low. Now, let's develop a linear regression project together. First, we import the necessary libraries. We will use pandas to read the CSV file. We will use Seaborn and Matplotlib for visualization. We will use ElasticNet model and linear regression model. After adding the evaluation metrics we will use, let's import our dataset. Our train and test dataset are separated. If it hadn't been separated, we would have separated it ourselves. Let's start with observing our dataset. We display the first 5 lines using the head function. This dataset includes the data about housing market, information such as the year the houses were built, the number of rooms, and the price is available. We learn the number of rows and columns with the shape function. We can see that there are 1094 rows in total. We can see more details with the info function. We see that the data types are integer and there are no null values. Our goal when working with this dataset will be to estimate the sale price value. Therefore, we will set this value as target. The other column values will be our features. We delete the sale price values from the X values by dropping them. X contains features. We choose sale price as the Y value. We did this for both our train and test datasets. Now, let's move on to training the model. We will use linear regression model. We will also use another model, ElasticNet, for comparison. The for loop I wrote will run sequentially for both models. We do the training by giving the train dataset to the fit method. Then we give X test values and enable it to make predictions with the predict method. Now, let's calculate the evaluation metrics. We compare our predictions with Y test values. I rounded it with the round function to make it easier to read. As you can see, the ElasticNet model is more successful. Of course, there is not much difference, but we are trying to get the best results. MAE, MSE, and RMSE values of the ElasticNet model are lower. Also, the R-squared value of the ElasticNet model is higher. Consequently, we trained our regression models and got pretty good results. Better results can be obtained by using different methods. The model we trained successfully predicts the price on the test dataset that has never been used as input before. Let's create a correlation matrix to see the relationships between the variables in the dataset. Each variable is highly correlated with itself and has a correlation value of 1. This is called positive correlation and is a normal situation. Positive correlation means there's a positive linear relationship. So, as one increases, the other also increases. It's shown in the red in the figure. You can see the color scale on the right side. We see that some correlation values are close to -1. These are called negative correlations. Negative correlations are shown in blue. Negative correlation means that there is an inverse linear relationship. That is, one increases while the other decreases. Correlation values close to 0 mean that the correlation is low. In other words, there is no linear relationship between two variables. When we examine the relationship between the sale price value and other features, we can see positive and negative correlations. Thanks to the correlation matrix, we can identify the features that have the most impact on predicting the sale price value. When we examine the sale price row, we see that the highest correlation belongs to the overall quality feature. That's it for regression. See you in the next video.